Quantum mechanics deals with the behavior of matter and light on the atomic and subatomic scale. It attempts to describe and account for the properties of molecules and atoms and their constituents electrons, protons, neutrons, and other more esoteric particles such as quarks and gluons. These properties include the interactions of the particles with one another and with electromagnetic radiation, i.e. light, X-rays, and gamma rays. The study of quantum mechanics is rewarding for several reasons. First, it illustrates the essential methodology of physics. Second, it has been enormously successful in giving correct results in practically every situation to which it has been applied. There is, however, an intriguing paradox. In spite of the overwhelming practical success of quantum mechanics, the foundations of the subject contain unresolved problems, in particular, problems concerning the nature of measurement. An essential feature of quantum mechanics is that it is generally impossible, even in principle, to measure a system without disturbing it. The detailed nature of this disturbance and the exact point at which it occurs are obscure and controversial. Thus, quantum mechanics attracted some of the ablest scientists of the 20th century, and they erected what is perhaps the finest intellectual edifice of the period. Historical basis of quantum theory. At a fundamental level, both radiation and matter have characteristics of particles and waves. The gradual recognition by scientists that radiation has particle-like properties and that matter has wave-like properties provided the impetus for the development of quantum mechanics. Influenced by Newton, most physicists of the 18th century believed that light consisted of particles, which they called corpuscles. From about 1800, evidence began to accumulate for a wave theory of light. At about this time, Thomas Young showed that, if monochromatic light passes through a pair of slits, the two emerging beams interfere, so that a fringe pattern of alternately bright and dark bands appears on a screen. The bands are readily explained by a wave theory of light. According to the theory, a bright band is produced when the crests and troughs of the waves from the two slits arrive together at the screen. A dark band is produced when the crest of one wave arrives at the same time as the trough of the other, and the effects of the two light beams cancel. Beginning in 1815, a series of experiments by Augustin Jean Fresnel of France and others showed that, when a parallel beam of light passes through a single slit, the emerging beam is no longer parallel but starts to diverge. This phenomenon is known as diffraction. Given the wavelength of the light and the geometry of the apparatus, i.e., the separation and widths of the slits and the distance from the slits to the screen, one can use the wave theory to calculate the expected pattern. In each case, the theory agrees precisely with the experimental data. In 1905, Einstein extended Planck's hypothesis to explain the photoelectric effect, which is the emission of electrons by a metal surface when it is irradiated by light or more energetic photons. The kinetic energy of the emitted electrons depends on the frequency n of the radiation, not on its intensity. For a given metal, there is a threshold frequency n0 below which no electrons are emitted. Furthermore, emission takes place as soon as the light shines on the surface. There is no detectable delay. Einstein showed that these results can be explained by two assumptions: one, that light is composed of corpuscles or photons, the energy of which is given by Planck's relationship, and two, that an atom in the metal can absorb either a whole photon or nothing. Part of the energy of the absorbed photon frees an electron, which requires a fixed energy W, known as the work function of the metal. The rest is converted into the kinetic energy mu2 of the emitted electron. Me is the mass of the electron and u is its velocity. Thus, the energy relation is if n is less than n0, where hn0w, no electrons are emitted. Not all the experimental results mentioned above were known in 1905, but all Einstein's predictions have been verified since. Basic concepts and methods. Bohr's theory, which assumed that electrons moved in circular orbits, was extended by the German physicist Arnold Sommerfeld and others to include elliptic orbits and other refinements. Attempts were made to apply the theory to more complicated systems than the hydrogen atom. However, the ad hoc mixture of classical and quantum ideas made the theory and calculations increasingly unsatisfactory. Then, in the 12 months started in July 1925, a period of creativity without parallel in the history of physics, there appeared a series of papers by German scientists that set the subject on a firm conceptual foundation. The papers took two approaches: one, matrix mechanics, proposed by Werner Heisenberg, Max Born and Pascual Jordan, and two, wave mechanics, put forward by Erwin Schrödinger. The protagonists were not always polite to each other. Heisenberg found the physical ideas of Schrödinger's theory disgusting, and Schrödinger was discouraged and repelled by the lack of visualization in Heisenberg's method. However, Schrödinger, not allowing his emotions to interfere with his scientific endeavors, showed that, in spite of apparent dissimilarities, the two theories are equivalent mathematically. The present discussion follows Schrödinger's wave mechanics because it is less abstract and easier to understand than Heisenberg's metric mechanics. Schrödinger's wave mechanics. Schrödinger expressed de Broglie's hypothesis concerning the wave behavior of matter in a mathematical form that is adaptable to a variety of physical problems without additional arbitrary assumptions. He was guided by a mathematical formulation of optics in which the straight-line propagation of light rays can be derived from wave motion when the wavelength is small compared to the dimensions of the apparatus employed. In the same way, Schrödinger set out to find a wave equation for matter that would give particle-like propagation when the wavelength becomes comparatively small. According to classical mechanics, if a particle of mass m is subjected to a force such that its potential energy is Vxyz as z at position xyz, then the sum of Vxyz and the kinetic energy P22 m is equal to a constant, the total energy E of the particle. Thus, it is assumed that the particle is bound -I.E, confined by the potential to a certain region in space because its energy E is insufficient for it to escape. Since the potential varies with position, two other quantities do also: the momentum, and hence, by extension from the de Broglie relation, the wavelength of the wave. Postulating a wave function Psxyz that varies with position, Schrödinger replaced P in the above energy equation with a differential operator that embodied the de Broglie relation. He then showed that PS satisfies the partial differential equation. This is the time-independent Schrödinger wave equation, which established quantum mechanics in a widely applicable form. An important advantage of Schrödinger's theory is that no further arbitrary quantum conditions need be postulated. The required quantum results follow from certain reasonable restrictions placed on the wave function, for example, that it should not become infinitely large at large distances from the center of the potential. Schrödinger applied his equation to the hydrogen atom, for which the potential function, given by classical electrostatics, is proportional to E2r, where E is the charge on the electron. The nucleus, a proton of charge E, is situated at the origin, and r is the distance from the origin to the position of the electron. Schrödinger solved the equation for this particular potential with straightforward, though not elementary, mathematics. Only certain discrete values of E lead to acceptable functions PS. These functions are characterized by a trio of integers NLM, termed quantum numbers. The values of E depend only on the integers n1, 2, 3, etc. and are identical with those given by the Bohr theory. The quantum numbers L and M are related to the angular momentum of the electron. Square root of LL1 is the magnitude of the angular momentum and is its component along some physical direction. The square of the wave function, PS2, has a physical interpretation. Schrödinger originally supposed that the electron was spread out in space and that its density at point xyz was given by the value of PS2 at that point. Almost immediately, Born proposed what is now the accepted interpretation, namely, that PS2 gives the probability of finding the electron at xyz. The distinction between the two interpretations is important. If PS2 is small at a particular position, the original interpretation implies that a small fraction of an electron will always be detected there. In Born's interpretation, nothing will be detected there most of the time, but when something is observed, it will be a whole electron. Thus, the concept of the electron as a point particle moving in a well-defined path around the nucleus is replaced in wave mechanics by clouds that describe the probable locations of electrons in different states.